The second section of the course, was on applications in geometry, in approximation in statistics, areas like that. And this last section of the course is on numerics and algorithms. How do you actually solve these problems? Now, you have been solving these problems for the last two parts of the course. You've been solving these problems. But presumably at this point you don't know how it's done. And the main goal of this section, whole section of the course, is to demystify how it is that we solve these convex problems, right? So that's the idea. Now, most of you are not going to write your own solvers, right? Actually, some of you might have to. If you go into areas where the problems are absolutely gigantic, something like CVX is not going to work. You're going to have to develop your own solver. Or if you go into like real-time systems where you need to be able to solve optimization problems in microseconds, again, something like CVX is not going to work for you, and you're going to really have to know how it's done. I should say a couple more things about that. I still believe strongly, it's not just a question of demystifying it, but I believe it's very important for everyone to know a little bit about how these problems are solved. And specifically, what you want to know is the link between problem structure and how fast we can solve it. So that's really, if there was one takeaway for the entire last part of this course, it's to understand that one thing. You should be able to look at that problem and say, ooh, that's got 100,000 variables, but I can solve that super fast because I recognize the structure. So that's what this whole section of the course is about. Now we're going to go back today and start, well, at the very beginnings. We're going to talk a little bit about numerical linear algebra. Some of you probably know this, others of you probably don't. People who have used things like MATLAB have certainly been using this as a user, as a consumer, but you may not know actually how it's done. And what we'll do today is just look at the basics. And I should also say how it fits into the big picture. So the big picture is, this lecture, we're going to talk about how do you solve linear equations. So that's fine, and there's a finite algorithm for that, and we'll look at how that's done, and we'll see how it's done. It's Gaussian elimination. You've been doing this since high school, I assume. Okay, then I'll tell you how this fits into the rest of the course, right? So in the rest of the course, we'll see how do you minimize. We'll start by talking how do you minimize a smooth function. We'll start with how do you minimize a quadratic function? Well, you set the gradient equal to 0. But the gradient of a quadratic function is a linear function. And so minimizing a quadratic function is solving linear equations. So if you like, you can think of this whole stuff we're going to look at now, how do you solve linear equations, as how do you minimize a quadratic function? So that's the optimization connection. Okay, so we'll first start by talking about matrix structure and algorithm complexity. Matrix structure is, some things are obvious, like what is, diagonal matrices, identity matrices, sparse matrices. We'll talk about that. Then we'll talk about the dominant method used to solve linear equations, and that's using factored matrices. So you'll factor a matrix and then do a sequence of solves with the factors. We'll talk about some very famous factorizations, the so-called LU. That's going to be for lower triangular, upper triangular, the Cholesky factorization, and something called the LDL transpose factorization. There, L is lower triangular, D is diagonal, and L is upper triangular. Actually, we'll see in some cases D is block diagonal. Then we'll look at a general construction called block elimination and the matrix inversion lemma. And this is something that shows you how it is that you can solve sometimes absolutely enormous sets of linear equations very efficiently by exploiting some structure that's present. So first, let's just start with solving AX equals B, where A is n by n. Okay, and in fact, let's say on that laptop right there, that's not mine, but I know the number. I want to ask you all, how long do you think it takes to solve the equation AX equals B, where X is size 1,000? Before you say anything, I want to point a few things out. That's solving 1,000 equations for 1,000 variables. The size of A is 1,000,000 coefficients. Everybody got it? Okay? And now what I want to know is, how fast can I solve it? The answer was 30 milliseconds. Okay, and I happen to know the number on that thing is about 10. Okay, so actually, this is an amazing thing, and it's actually worthwhile for all of us to sit and think how unbelievably amazing that is, right? I mean, that's ridiculous, right? That's something that takes like a billion, we'll see, it takes, generic methods take a billion operations. It's 10, 15 milliseconds on that. Okay? It's got multiple cores, does all sorts of things are happening to make that number, but just the idea actually that it's less than a second is unbelievably impressive. Okay? So, well, we'll get to that. So basically for general methods, right? General methods means you're exploiting nothing in the matrix A. Absolutely nothing, right? All the entries are assumed to be non-zero. There's no particular structure. A structure would be something like A might be a discrete Fourier transform or a discrete cosine transform. In which case, of course, you can solve it faster than n cubed. You can solve it in like n log n. Okay, so that would be structure. Other structure would be sparsity, right? That would be that A has a lot of zeros, right? One definition of sparsity goes something like this. It's a matrix that has enough zeros that it's worth your while to take advantage of it. That's some 1960s definition. I mean, it's a perfectly good definition, right? So, okay. So general methods, it says that these things grow like n cubed. Oh, so for fun, how long would it take that laptop there to solve, say, 100 equations in 100 variables? That's 10,000 coefficients in the matrix. So the answer was what? 30 microseconds. Thank you. Okay, great. Okay. So, I mean, that's ridiculous. By the way, this also hints why you should know about all these things, right? These numbers are so ridiculous that it means that these things can now be embedded on all sorts. It means the amount of computation you can do is unbelievable. You can put stuff, you can actually embed, all these things can be embedded. They can, in things that would normally take like seconds to run, can run in milliseconds. They can be embedded in things. I mean, crazy stuff can happen. So, okay. All right. So basically for general the generic methods, this grows as n cubed. And I'll tell you what the generic methods are shortly, what they are. And this is the part that I think I want everybody to know. When A is structured, and we'll talk about all sorts of structure, it's way faster, or generally substantially faster than n cubed. Okay, and structure is stuff like banded. A banded matrix is one where basically Aij is 0 if the difference between I and j is big enough, bigger than some threshold, right? Systems like that can actually be solved in linear time. Okay, so I mean, these are just things you wouldn't. I mean, unless you knew this, it's not obvious, right? So what that says is I can solve 1,000,000 variables with 1,000,000 equations on that laptop. Actually, I can do that on my phone, but I could on that laptop I can solve a system of 1,000,000 equations, 1,000,000 variables, if it's banded with a bandwidth of like 5, right? And not only that, I can solve, I mean, unbelievably fast. I won't do the calculation now, but it'll be shocking. Okay? And if you didn't know that, you'd think, well, that's a big hard problem or something. You'd multiply it by n cubed. Okay. So what are the basic ideas? Well, this goes back to the 60s. It's still sort of relevant. It's less relevant than it was. I'll say a little bit about that, but it still is not a bad indicator. So basic concept is a flop. That's supposed to be a floating point operation. And roughly it's something like an addition, a subtraction, a multiplication, division of two floating point numbers. Now there are some older definitions where it's an addition plus a multiply. And you might include things like square roots in there. All of that is nonsense because square roots cost like 50 times more. A division is something like costs you 20 times more than an add. So for a lot of these things, the key idea now is just to take the numbers too seriously, right? They're to be considered to be within a factor of 10, right? And that's the right number. The flop was invented sort of when, main CPUs didn't do floating point arithmetic, and they basically had to like send a message over to some giant board that was like your floating point board, and all sorts of stuff happened, and then when that multiply was finished, right, something would come back. Everybody, and so in that setting, sure, counting the number of flops made total sense. It's ridiculous now, right? Because with the number of, there's all sorts of things you could do there. Not even getting into like minor details, but you can do crazy stuff all in parallel and stuff like that. So, okay. All right, so the idea, and this traces to the 60s and is still actually somewhat relevant. It goes something like this. To estimate the complexity of an algorithm, what you do is you express the number of flops. Usually it's a polynomial. It's a polynomial function of the problem dimensions. And then what you do is you drop all but the leading terms, right? So, if it's something like, 1/3 n cubed plus 2n squared plus blah, 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 something like that, you just say, well, the complexity is 1/3 n cubed. And honestly, these days, the 1/3 doesn't make any difference at all because you're not shooting for, factor of 2 is ridiculous. You could not predict using these methods, right? Factor of 10 is the right amount. Now, this is not an accurate predictor of computation time on modern computers, right? You can get it within a factor of 10 in the absence of certain bad things. And actually, if things are done really well, right, like if it's optimized code, it once again becomes a reasonable predictor. So it's kind of an interesting thing. But it's very useful as a rough estimate of complexity. It still gives you that, right? But do not come along and say, oh, this one is half the number of flops, therefore it must run faster or something. I mean, things like your access pattern and locality of reference in memory are way more important than factors of 2 and flop counts and things like that. So, okay. I mean, another nice thing is a lot of these things are done for us by people who know what they're doing, namely those who write like compilers and things like that. So that's the good news. Okay. So let's look at some operations. And this is a conceptual division into vector, matrix, matrix product. And I should say this is something you should probably all know about. There's no reason not to. There's something called BLAS, and it traces to the 60s, 70s. It's called, it stands for Basic Linear Algebra Subroutines, right? And believe it or not, the standards of these are written in, Fortran. That gives you a rough idea, okay? And by the way, still. And then they have, of course, these have been re-implemented in all sorts of real languages, actually. So anyway, so it's basic linear, and they call these things, this is called BLAS level 1, this is BLAS 2, and that's BLAS 3, right? But you don't need to know that, but actually that's not true, right? An educated person just knows these things. You don't have to know the details of these things, but you should know that there's BLAS level 1, BLAS level 2, and BLAS level 3. And I'll say a little bit about what they mean and why it's important to know about. Okay, so vector operations. This would be something like, calculating an inner product, right? So you calculate an inner product, you can count the number of flops. It's like 2n minus 1 flops, 2n if n is large, right? So that's something like that. So you'd say it's order 2n or something like that. Another one would be like a sum, something like that. By the way, if you're taking an inner product, it would also depend if the vectors are sparse, then needless to say, this could be way faster, and it actually depends, quite a bit on, the data structure you use to describe sparse vectors and things like that. So, okay. The other thing I should say about an inner product, just to give a hint sort of about modern stuff, is something like an inner product is easily parallelizable, right? So on a modern, on some modern platform, it'd be divided up. If you do an inner product 2 million long vectors, you'd have multiple threads, and each one would be taking inner product of chunks, and then those would be added together and things like that. So I'm just saying that's by the way how you get the 20 millisecond, 30 millisecond numbers to solve 1,000 equations on that laptop. Okay, so but it's not bad. So if you want to think of something serially stepping through, like please get me the next xi, please get me the next yi, please multiply them together, and then plus equals that onto some your inner product plus equals xi, yi. If you want to think of that, go ahead. It doesn't hurt. It's charming. It's simple. But you should understand that it's not how it works. Unless you write the code right like that, right? In which case it'll run whatever 10 times slower. Right. So okay. All right. Next one is matrix vector product. That's y equals ax. So here you multiply a matrix by a vector. And what is it? Well, there's many ways to think of it, but one way, if you're just counting flops, it doesn't matter, is that it's basically you take the inner product of each row of A with x. Okay? So it's basically calculating m inner products in Rn, and that's something like 2mn, right? And you forget the 2. This is like, that's a joke, right? It's order mn. right? So it's the number, it's basically the number of entries in A. Now, if A is sparse, this is obviously a whole lot less, right? But actually how fast it is quite a complicated topic because it depends on exactly what data structures you use to represent the sparse matrix and all sorts of stuff like that, right? But again, it's not easy, at least without getting into the details, to realize that if a matrix is a million by million with maybe 10 million non-zero entries, you only have to multiply it by the 10 million non-zero entries, right? So, okay. And it can be less if it's structure. So, for example, here's one. If I gave you the matrix A as a low rank product, right? So if I gave you the matrix A, let's suppose A is a million by million, but I give it to you as a million by 10 multiplied by 10 by million, right? So this is what you'd get if you ran PCA or SVD or something like the low rank approximation. Number one, you'd actually be able to store it. You can't store a million by million matrix, right? So, but you could store it this way. And the multiply would certainly not be a million squared. It would be way less. It's order of a million. In fact, it's like 20 million times that because it's 10 by 10. Everybody got this? Right. So, okay. Then you get BLAST level 3. These are matrix products. So that means multiply two matrices. I mean, that's the canonical one, is multiply two matrices. And here, it's actually the product of the dimensions, basically, right? If these are like m by n by p, it's m and p. So it's the product of the dimensions. Okay. Now, if they're sparse, it's much less. And you get different things. If they're symmetric, you can divide things by 2. I mean, that typically doesn't matter, but that's the idea. And now, this is probably where I mean, again, these are not things, we're not going to go into these details, but I'll just say a little bit about it so that you appreciate it, right? So everybody here knows how to multiply two matrices, right? I mean, you could write a 5-line C program that would do this. Everybody here could, right? It'd be completely trivial. It'd be like, how do you get CIK? Well, you walk along A and you walk along B and multiply the associated entries and then add it all up, right? So you could write a 5-line C program, right? It'd be a bunch of 4s and wouldn't even be 5 lines, probably. It'd be 5 lines with a lot of comments. Okay. And you can compile it. And of course it would do like, whatever, 2 MNP flops by the time it runs. In fact, if you were to use LAPACK, that's the, again, this is just for cultural background. You do not need to know this, although it's not bad to know it. Okay, so LAPACK this is an open source package of linear algebra routines, and multiplying two matrices. It doesn't seem like there'd be any. If you don't think about this, it doesn't seem like there'd be any subtlety there, right? We all know what CIK is. It's sum over J, AIJ, BJK, right? I mean, it doesn't look like there's a whole lot of room for optimizing there, right? I can give you something more complicated like sorting or something like that, or finding the shortest path, but then you can imagine somebody smart could do something better. Everybody see what I'm saying here? I mean, come on, calculating the product of two matrices, one person's implementation, you can beat a naive one by a factor of 100? That doesn't seem right. Does anyone know actually how that's done and why? It's actually kind of interesting. I mean, this is just for cultural background, but it's good to know. Here's how you multiply two 1,000 by 1,000 matrices. Here's how you do it if you use this package. What happens is 1,000 by 1,000 matrices are broken down into things like 10 by 10 block matrices with blocks that are 100 by 100. Everybody following this? Now, matrix multiplication you can do blockwise, right? So what that says is you end up multiplying 200 by 100 matrices by blocking them, and then each block you do 100 by 100 multiply. Okay. Now, how do you do 100 by 100 multiply? It's blocked down to 10. So each of those is a 10 by 10 matrix of 10 by 10 matrices. Everybody got this? And then, so what's really happening is you're doing giant piles of 10 by 10 multiplications. And by the way, the parameters 10 I made up are totally made up, and it would differ, depends on your architecture, right? Okay, so that's called blocking. And the idea behind blocking is you can arrange it if you do it just right. If the blocks are the right sizes, like that 10 by 10 multiply might happen in, the 10 by 10 multiply might happen with registers or something, right? And then the 100 by 100 might just fit in L1, right? And stuff like that. So if you do this right, if you do your blocking right, then and not only that, you could do part of it in parallel and stuff like that. If you have multiple cores, somebody's multiplying these, somebody's multiplying these. You exploit all this stuff, and that's actually how matrices get multiplied. Okay, at least on a on sort of a modern processor, right? So that's the idea. And if you want, and the memory access pattern is such that there are never cache misses. And by the way, how do they choose the block sizes? That's it. They have something called Atlas, right? It's really kind of cool. I mean, you don't need to know any of these things, right? But it's sort of fun. That's automatically tuned linear algebra software. This is all open source stuff. And what it does, it takes your computer and it just says, well, I'll try 10, right? And it does it, and it factors matrices for a while, and then it says, I'll try blocking it as 9 by 9. It tries 9, it tries 11, it tries 12, and then it just does bisection, or it just tries a bunch of them. And half an hour later, it's decided on your architecture what the right what the right blocking sizes are. Okay, completely empirical. Everybody got this? So, and when you see these curves, they're absolutely amazing. It would be things like, you'd see something going like, here's a function of n, and say it would be looking like that. That's a log-log plot, and then all of a sudden you'd see this, right? And you'd say, and by the way, what would this be? Yeah, so this is something that's just barely fitting in some cache, right? And this is something that this is called bad blocking. This is where your block sizes were exactly, a handful of things too big to fit in some cache. So basically, it's a disaster, something like that. In fact, this can even go down. That's the cool part. It just can be non-monotonic. But anyway, okay. All right, so that's like way more than you need to know about all this, but it is good to know. Actually, it is good to know, even if your interests are quite theoretical or mathematical. This is good to know because if you do theoretical or very mathematical things, this is how it hits the road. It hits the road right here in LAPACK in most cases. Well, except in giant sparse things, but we'll talk about that. But a lot of times, you do some cool statistics, you do anything, you do machine learning, it's this. Now we're going to talk about solving linear equations. And the one way to do it is we'll first talk about classes of matrices where solving AX equals B is easy. And then there's a simple trick that puts it all together. So one would be this, diagonal matrices, right? So if A is diagonal, then solving AX equals B is simple. By the way, one interesting thing is when people write A inverse B, mathematically, it's what you mean. That's what X is. But it is universally understood, even if people write it in an algorithm statement, that you do not parse it this way, A inverse times B, because that would suggest code like, A dot inv, times B. And except in extremely rare cases, you would never compute it that way, right? So A inverse B is sort of like a phrase that when someone describes an algorithm, you should see, and it doesn't mean form A inverse and multiply it by B. Mathematically, the semantics is identical, but you should understand that this is so common. And people will even say things like inverting that matrix is easy, and they don't mean inverting the matrix. They mean solving the equation. Okay, so this is just so, okay. So here, computing A inverse B, if A is diagonal, I mean, it's incredibly easy. It's just you divide. It's n flops, rough, whatever it is. Okay? The next one is interesting, right? It says that a matrix is lower triangular, right? And so that says, it looks like this, A11, A21, A22, something like that, okay? And you're multiplying this by, x1 up to xn, and that's supposed to be, b1 up to bn, okay? And yeah, how do you do this? You look at the first row. The first row says A11 x1 equals b1, so x1 is obviously a b1 or a11, right? Oh, and by the way, what exception do you throw if a11 is 0? What if you have divide by 0 exception? What? Yeah, you throw a message back, which is like a singular. So I'm not going to calculate A inverse B for you, right? So, okay. So, so once you know x1, right? And there's lots of ways to think of this. Once you know x1, the second row says a21 x1 plus a22 x2 equals b2, right? But you know x1. So you just plug in that value, subtract it on the right, and then divide by a22. So the algorithm looks something like this. And you can sort of calculate the number of flops. I mean, it doesn't matter, but you can kind of get a rough idea what it is. This thing is kind of growing. And it's got a great name. This is forward substitution. And the reason it's called forward substitution is you calculate xi, and then xi, from then on, you substitute that value into the equation, right? And so you can see you do kind of like length 1, length 2, length 3, length 4, and it's growing. And you know that the sum of those numbers is something like the square over 2, right? And if you do it exactly right, it's just like n squared, right? If you count flops. That doesn't matter. It's n squared flops. Okay, and that's called forward substitution. And there's a similar one if a matrix is upper triangular. And what do you imagine it would be? You know, it's the same thing. It's it's backward substitution, right? You start by getting xn first and going backwards. Okay, so these are just completely simple. There's nothing complicated here. This is really interesting when A is sparse, because when you have a lower triangular sparse matrix, I don't know, go ahead and give me a rough number. So for a sparse matrix, and a very important attribute is number of non-zeros, sometimes written NNZ. Okay, so I just roughly, if I have, in terms of the number of non-zeros, how many flops does it take to do forward or backward substitution with a lower triangular, upper triangular matrix that's sparse in terms of the number of non-zeros? What is it? Yeah, it's linear. It's actually equal, kind of, to the NNZ. Everybody got that? Right? Because basically, each of these coefficients appears once, right? And so it's about linear, right? So that means if I have a million by million matrix, right, with, let's say, 50 million non-zeros, that's, an average of 50 non-zeros per row or column. That's 50 million flops. How fast can I do it on there? Just rough order magnitude. You can assume that's between 1 and 10 gigaflops, right? Something like that. So the answer is milliseconds. Okay? So that was to solve lower triangular equations million by million, right? With like 50 non-zeros per row. Okay? So that's a rough idea, right? So don't worry, we're going to assemble all these things in a minute. Okay. So that's upper triangular, lower triangular, diagonal. Another one would be orthogonal. So if a matrix is orthogonal, then in fact, computing A inverse B is the same as A transpose B, right? So it's just a matrix vector multiply. It's order n squared in general. But it turns out it actually depends how the orthogonal matrix is stored. There are other data structures. Here's a very famous one. It looks like this. It's a reflection, right? That's an orthogonal matrix. And you can see it is an identity minus a rank 1 matrix, right? We're going to talk a lot about that later today. But so there, that can be done in order n flops, right? So very fast, right? So for example, it's not completely standard, but it would occur often, is one data structure for representing an orthogonal matrix is as a product of these things, these reflections here. And you would actually give them, you'd give the u's. You'd give u1, u2, u3, u4. And you can see that actually, it would be the same to multiply by the transpose, which is the inverse. Each of those would simply be linear in that data structure, right? Okay. And a final one is permutation matrices. So a permutation matrix, well, this is kind of silly, right? If I solve, P x equals b, all I do is permute the entries, right? And actually, by this 1960s version of things, when you say how many flops is that, the answer is 0, because there's no floating point. You're just copying. You're copying. I guess all you're doing is you're copying. Whatever it is, 8 bytes, or how many bytes is a double? 8. So you're copying 8 bytes from here to there and around like that. So, and oh, by the way, if that's a 100 million long vector and the access pattern is completely random or whatever, you could end up with, this could be it could be 0 flops and actually take some time. Okay, everybody? All right. Okay, so, all right, and now we get to how you solve AX equals B. And it's a general method. It's the high level is it's factor solve, and there are some very important things actually to know about it. And if you haven't seen these stuff before, you'll learn something shortly, and it'll be quite real. It'll be something you should know, and it's not expected. So the idea is this. There's two steps. There's factor and there's solve. And factor says you take your coefficient matrix and you factor it as a product of simple matrices. By the way, you've seen tons of things like that, like SVD, eigen decomposition, eigenvector, you've seen lots of these things, right? QR factorization. All right, so what you do is you factor it as a product of simple matrices. Sometimes it's two, it could be as few as two, and it could be as many as 4 or 5, right? Actually, sometimes it can be a variable number where some of those things have exotic data structures, like it could be these products of reflections, right? Okay. So, well, one example is you can actually understand the FFT this way. I don't know if people know. If you know what the FFT is, great, and I'll say what it is. It's a specific matrix. It's the DFT matrix, the discrete Fourier transform. It's a van der Waals matrix with a bunch of complex numbers in it. Do you know what I'm talking about? Fine. It basically calculates a discrete Fourier transform. And there's an interesting thing where you take an order n matrix like that, and you can factor it into a product of log n matrices which have very specific sparsity patterns, okay? And it turns out if you do this and then exploit some of the structure, you get an n log n factorization. Okay, so, all right, let's move on. So these are things like, you know, diagonal, upper, lower triangular, and so on. And then, I mean, this is totally obvious. What is A inverse B? Well, I mean, the inverse of a product is just the product of the inverses in the other order, like this. And then you parse it. This is extremely important this way. Remembering that you're never computing any of these inverses, right? You parse it this way, right? So you should actually think of that as a method, A1 inverse, that you call on B. So that's what happens. So you unwind, right? So you write A as a product. How do you calculate inverse B? You call the inverse methods from backwards, right? And you just unwind everything. So it looks like that's the idea, right? So that's the idea. Now, this immediately has some pretty cool implications. It says the following, and this is like very important. It says that suppose you need to solve a bunch of equations with the same coefficient matrix but with different right-hand sides. Okay, that comes up in tons of places, right? I mean, boy, tons, right? So suppose that's your problem, right? And by the way, you'll see tons of cases where this comes up. Okay, then what it says is you factor the matrix. That typically costs more. We'll talk about that in a minute than the solve, right? So you factor it and you cache the factorization. And what that means is it says that if you want to do multiple right-hand sides, you get one factorization here and m solves. Okay? So for the most common methods, by the way, solving linear equations, the factor costs n cubed, the factor step, and the back solves cost n squared, the solve steps. Okay? And now I'm going to ask you a question. To solve 1,000 linear equations with 1,000 variables on that machine is, I'll just make up a number, we'll fix it as, I like your number, 30 milliseconds. It's 30 milliseconds, okay? And I want to know how much time does it take to solve 2 equations? AX equals B1, AX equals B2 with the same A. It's 30 milliseconds to do 1. How many is it to do 2? By the way, the naive method just calls solve AB twice. And the answer is, what do we decide, 30 milliseconds? 60 milliseconds. And what is the correct answer? 30. It's 30, okay? All right, how many does it, so by the way, that's pretty weird. Everyone got that? That the cost of solving 2 linear equations, if you cache the factorization, is actually the same as 1. And I don't think this is obvious, frankly. It is not obvious unless you knew this, right? It's an absolutely real phenomenon, and it's the key to tons of things, okay? Tons of things being sort of either viable or not, right? How much would it cost me to solve, let's say, 25 linear equations, 25 different right-hand sides, same A, on that laptop? I'm doing 25 times more work, and the time is the same? The answer is yes, because the factorization dominates everything. Once you factor, you can solve. Okay, so I mean, these are things. Yeah, if whatever your background is, you didn't know it, now you know it. This can actually have a huge impact on all sorts of stuff. So let's look at some factorizations. By the way, I'm not going to cover factorizations here. So that's an entirely different topic. They're not that hard, actually, to work out how these factorizations go. It's a whole world in itself. But this is just so you know at the highest level, we can't go into the details of factorization. So here's the most famous one, is LU factorization. And by the way, it's completely equivalent to Gaussian elimination. It says any non-singular matrix you can factor as PLU, where P is a permutation matrix, L is lower triangular, U is upper triangular, and obviously L and U have to have non-zeros on their diagonals, because if there was a 0 on the diagonal of L or U, what would happen? Yeah, A is non-invertible. The determinant is 0, and so you have no right solving AX equals B. Okay, and this factorization, we're not going to go into it, although it is just Gaussian elimination. The cost is order n cubed flops, right? So that's how that works, okay? And so here it is. Here's how you solve a set of linear equations by LU factorization. So you're given A and B. The first thing you do is you factor A as PLU. That's n cubed flops. You then how do you solve? Well, you go backwards, right? So you solve PZ1 equals B. That's like 0 flops or whatever. I mean, whatever you like. You're permuting the entries of B, right? Then you do forward substitution, back substitution. And you can see this is like 2n squared, right? And so, I mean, the numbers don't really matter here, but the point is n is typically big enough. N would have to be tiny before, like 10 or something, and then all of this is off anyway. But n would have to be, so if n is any reasonable number, 100,000, something like that, then the n cubed thing is bigger, right? And so that's the idea. And so it's basically about n cubed, right, is the complexity. Okay, so that's LU factorization. The back solve, notice, is order n squared. So in fact, you would say the following. Let's see, how shall I put it? Okay, here's a good way to conceptualize it. One way to think of solving AX equals B for different right-hand sides is something like this. The first time you solve it, it costs you n cubed. Thereafter, after you factor A and cache it, you get a discount by factor n. Everybody got that? Right? So the first one might take you half a second, and then the next one is going to take you sub-millisecond, right? I mean, so these are actually very important things to know about. Okay. Now, sparse LU factorization. This is quite interesting. All right. And I mean, I'm not going to go into the details, but this is actually very good stuff to know about. If you have a sparse matrix A, the most common factorization method is to factor it into a product of 4 matrices. And by the way, they have other names for these. P1 and P2 are sometimes called like row and column permutations or something. But that's because that's what they do. That is, you factor it into a product of 4 things: a permutation, L, U, P. Okay. Now, the fact is, mathematically, you only need one of those permutations to ensure the existence of a factorization. Right? That's mathematically, because it follows from the previous one, right? The reason you would use 2, and the reason you would use a permutation both on the left and on the right, is that the what's actually happening here is this, is P1 transpose A, P2 transpose, right, is LU. So what you're really doing is permuting the rows and columns of A and then calling an unpermuted LU factorization on it. Okay? Now, by the way, if you choose P1 and P2 wrong, LU factorization doesn't exist, right? So let's assume you've chosen them correctly and they work. It turns out if A is sparse, the sparsity pattern of L and U depends on the permutations. Okay? So if you pick a good permutation, L and U are quite sparse, and that, of course, is going to affect your solve time, because your solve time, we've already looked at that. Back and forward substitution is basically n and z on L and n and z on U. Right? That's the number of flops. So the point is, if I pick one permutation P1 and P2 so that L has 1,000,000 non-zeros, and I pick another one so that L has 100,000,000 non-zeros, right? It's not just a memory issue, but also a runtime. Everybody see this? So anyway, so this is actually quite fascinating. It turns out that when you do an LU factorization on a matrix, right, then the permutation can have a huge effect on the sparsity of the result. How do you choose P1 and P2? Well, you can ask lots of questions. For example, obvious question would be, how do you choose row and column permutations of a sparse matrix so that its LU factorization has the fewest number of non-zeros? It's a totally natural question, and it's NP hard. Okay, so fine. So what do people do? Well, so it means everything. These are all heuristics. Okay, and actually they're more than heuristics, right? They're very stringent requirements, right? Because what people do who work on sparse matrices is the following. If you want to, so what happens is something like this. Well, you choose these entries using various methods, right? One of the methods, it depends on the sparsity pattern. It also depends on the values of A, right? That as you're going along, you might choose. So the P is actually built up while you're doing the factorization, okay? So that's how this works. And I'm not going to go into any details, but that's sort of the idea. And it's worth knowing about this. Okay. And what's the cost? Well, it's usually way less than n cubed, right? By the way, if it gets even close to n cubed, it means you have implemented an extremely inefficient method when you should have just called a dense LA pack routine, right? Which would have blocked everything nicely for you. That's all it means, right? But this is a big deal. If you're lucky, this is actually a very big deal. By the way, everyone here is a beneficiary of this. I can tell you that right now. And the reason is very simple. CVX, for example, calls SDPT3 or SEDUMI. All of these things use sparse matrix methods to actually do the heavy lifting. That's if you profile any of these solvers, that's all they're doing. The only thing they're doing is solving linear equations. There's nothing else. And they're literally solving AX equals B. Now, A is symmetric, but that's another story. It doesn't matter. Same idea goes, right? And they're all and they're exploiting sparsity very heavily. Okay. Now there's a little. I mean, it's a bit funny, right? Because if someone comes along over your shoulder when you're fiddling with CVX and someone says, "What are you doing?" You say, "I'm doing convex optimization," and they go, "Well, how do you know it works?" And you go, "Oh, that's the whole point. It's like it's tractable. I mean, we can do that. I mean." I had a whole course, and that was the whole point. There's other problems you can't solve, but these you can really solve. As a practical matter, the only reason you can solve them, as a practical matter, is because the heuristics of choosing the permutations for solving linear systems of equations are so good. Everybody got that? By the way, do not tell anyone outside this class that. Right? This is a secret we keep together here. Right? So if anyone asks you, why does that work? Is that heuristic? You say, absolutely not. This is not a heuristic. And in theory, it's not, right? If the worst thing that can happen is your permutation fails spectacularly and you revert to n cubed. That is not good if n is 10,000 or 50,000, right? So, but now you know, this is why, roughly speaking, you can solve equations. 10,000 variables, 100,000 variables, 1,000,000 variables, million by million. You can kind of solve sparse equations. And so the correct way to say it is if the God or gods, who control the heuristics of permutations used in sparse factorizations are smiling on you. And that depends on the offerings you've made to them lately. If they're smiling on you, then you can solve equations that would just otherwise be completely and totally out of the question. Everybody got this? Right? By the way, there are some sparsity patterns where you don't have to rely on the gods of heuristic permutation selection algorithms. Okay, then we'll talk about some of them. Well, I tell you one right now. If a matrix is banded, you don't need to make any offerings at all. It's really going to work always. Okay, but for general sparse matrices, this is not true. Okay, so but this is very good stuff to know about, even if you're more interested in sort of more theoretical stuff. This is very good stuff to know about. So now, what we're going to encounter more, what we're going to encounter is actually things that are generally not just square, but you actually have sign structure, right? So there's the Cholesky factorization. If you have a positive definite matrix, A, then you can factor it as LL transpose. And if you like, you'd say, it's not, it says it has an LU, what it says is there's an LU factorization with L equals U. Well, kind of duh, or aesthetics tells you that, right? Because what's a matrix that's symmetric? Well, its transpose is the same, or you swap rows and columns, the same thing. So, of course, the U and the L, that's all this says. Okay? And L is lower triangular. And in fact, generally people require just to normalize that the entries are positive. One very interesting fact about Cholesky factorization is a numerical one. It actually is stable. Again, we're not really talking about that. It means you do not have to permute. You can say immediately that if you calculate that in double precision, you're not going to have any trouble, right? That your error, you can bound the error in L, stuff like that. As a practical matter, it just works. In this case, and the cost is 1/3 n cubed. And again, the difference between 2/3 and 1/3 is like Zippo in current things, right? Where cache misses is way more important than some factor of 2. But you get the roughly. I mean, this you save because, well, you don't have to calculate separately in an L and a U, right? You're just calculating one L. Okay, so how do you solve things by Cholesky factorization? By the way, this would come up in least squares, right? That's your most basic convex optimization problems. Least squares, you could do it by Cholesky factorization. So here you'd factor A as LL transpose, and you do forward and backward substitution, and the cost is about 1/3 n cubed. Okay, so that's the idea. That's Cholesky factorization. Now, sparse Cholesky factorization, it looks just like sparse LU, but there's actually a very critical difference, and I'm going to say what it is. And you probably don't need to know it at this level, but these are good things to know about. So here it is. As before, there's P1 and P2. You do pre and post multiply, or if you like, you could say that another way to write this is to think of it this way. First, you permute A, then call a Cholesky factorization on the permuted version, right? So that's a good way to think of it. Oh, and by the way, everybody has a different thing. Sometimes it's lower triangular, sometimes it's upper triangular. The permutation either goes like here or there. So you always, anytime you actually use something that does a factorization, you have to look at exactly what they mean by it. And it'll probably be different from these notes, right? So, but this is too bad. There's no standards. Okay, now here, you always have a Cholesky factorization, but the permutation can have a huge effect on the sparsity of L, and therefore on the memory required to carry this out. And second, and of course it also has, since the number of non-zeros in L is basically the flop count, it's going to affect the runtime. Okay. Now, unlike the sparse LU factorization, where you're actually choosing P1 and P2 as you factor the matrix, right? Because you're actually looking at entries, and you want to avoid numbers that are too small if you're going to divide by something. Here, it turns out that P can actually be chosen entirely on the basis of the sparsity pattern of A. Okay? So, in other words, you take the sparsity pattern of A. You don't even have to know what the numbers are going to be, right? You can make a graph out of it. That's a very common thing. And then you choose an elimination ordering, right? But you do this once, right? So that says if you're going to do something like solve AX equals B with different values of A multiple times, when A is positive definite, you can actually cache the permutation. I don't know if you got that, but the usefulness of this will be clear in about 2 weeks. You can cache the factorization. And that's the idea. Anyway, so the cost is usually way less than n and all that kind of stuff here. So that's how that works. Okay. Another factorization we're going to see is the so-called LDL transpose factorization, and that's this. If you have a symmetric matrix, not necessarily positive definite, you can factor it as LDL transpose, right? And D, P is a permutation matrix. L is lower triangular unit, so you'd have LII equals 0. D is block diagonal, and it's either got 1 by 1 blocks or 2 by 2 blocks, right? So, and you get sort of the same thing, right? So this would be one of the methods of sort of choice. Oh, and I think I can give you a rough idea of what backslash does in MATLAB. I mean, just roughly. It's something like this. When you type A backslash B, I think first it looks at the diagonals of A, and if they're positive, or it compares some entries quickly to see if it's possible that A is positive, symmetric positive definite, right? So it guesses that. Then it attempts a Cholesky fact. If it finds that it is, if there's some evidence that A is symmetric, And positive definite, like for example, if it has a negative on the diagonal, it doesn't do this because it's all over. It's not positive definite. So it attempts to do a Cholesky factorization because numerically stable and fast. Okay, but if it turns out A wasn't, then the Cholesky fails. Then it falls back and does something like an LU or something like that. I mean, this is roughly what it does, right? So, okay, and it won't do a sparse factorization unless A is like explicitly stored, flagged as sparse. Okay, now we're going to talk about something. It's about an elimination method, but it actually ties to a whole bunch of stuff. And it turns out it's actually kind of the same as selecting the permutation, but we'll get to that. So what we'll do is let's just take AX equals B and block it. So all we're going to do is we're going to write it as blocks. We're going to partition X. That'll partition B, and we're going to write it that way. So it's just two sets of equations. It's A11x1 plus A12x2 equals B1, and then A21x1 plus A22x2 equals B2, right? So that's it. I'm just let's see what happens. What you do is from the first equation basically is A11x1 plus A12x2 equals B1. And what you do is, assuming A11 is non-singular, right? You put this over there, then pre-multiply by A11, and that says that you can write x1 as a function of x2, and you get this, okay? And so the idea is now we're going to eliminate x1 from the system of equations, right? So all we do is we plug this value of x1 into this, right? By the way, this is actually just sort of like the substitution stuff, but with matrices, blocks, right? So what happens is if you plug this equation into that, right, you get A21 times this thing plus A22 times x2 equals B2. And when the smoke clears, that's a set of equations for x2, and you get this equation right here. Okay, so and you would say things like you have eliminated x1. Okay, this matrix you have seen before. That's a sure complement. Okay, and you've seen it in any legitimate class you've taken. Right? Because a legitimate class uses linear algebra, and then you can't use linear algebra and not see that, right? So you take a probability class, that's conditional, covariance or something. That's the conditional variance, covariance matrix, right? You take other things, take circuits, mechanics, anything, physics, this comes up. Okay, so that's the sure complement. So what it says is that when you eliminate a variable, a block, or variables, or a block of variables from a set of linear equations, you're left with a linear equation that involves the sure complement. Okay, so actually that's a good thing to know about. Okay, so by the way, you would form this matrix, you'd solve x2, and then you would recover x1 using that formula. Okay, and so here's a completely generic algorithm for solving this block equation, and it says this. It says, yeah, you're going to form this matrix. That's the sure complement. It's called S here, right? So you form this thing, A11 inverse A12. Now, by the way, that can be formed lots of different ways. Oh, let me ask that. How would you, if there were no structure in A11, and A11 was, let's say, 1,000 by 1,000, and suppose A12 was 1,000 by 10, please tell me how you would form A11 inverse A12. What would you do? So A11, 1,000 by 1,000, inverse times A12. A12 is 1,000 by 10. How do you calculate that product? It's a product. How do you do it? You factor A11 cache and do 10 back solves. Done. Perfect. Okay. So, all right. So, but people just write stuff like form A11 inverse A12, right? Assuming you know what you're doing. Okay. So you form the sure complement. Then you solve the sure complement equation, and then you use this equation to reconstruct x1. Okay, so that's the method. All right, and let's figure out how much it costs. Well, the answer is it's f plus n2s. That's the cost of factoring A11, and s is the solve step, right? These are the back solves, right? As you said, there's one factorization and some solves. Step 2 costs this, and what we're going to do here is we're just going to assume on the second step is dense. Because you can work it out when it's not, right? And then the last step is something that's, again, we're going to just assume it's dense, generic, nothing, and we'll just we'll solve that equation. And that's going to be, and and 2 cubed, right? And so the total thing looks something like this. Now, here's what happens. If you apply this method now to a matrix that has no structure whatsoever, then F equals this and S equals that. And you plug it into this formula and you get back actually exactly the fact there's no savings whatsoever. Okay? So that was a completely silly thing to do. I mean, it doesn't matter. That's how you do it, right? Actually, it's interesting because it shows you what blocking is, right? Because here, this is blocking 2 by 2. Now you can imagine what blocking 10 by 10 looks like. It's just this. Okay, so that's it. Here's where it's useful. When A11 has structure, right? So if the factor cost and the solve cost on A11 is low, then this delivers big savings. Here's an example. Suppose that A11 was diagonal, right? That means the factor cost is 0 and the solve cost is n1. That's just, you just divide, right? Then the number of flops is this, and this is absolutely amazing. So this says that if you see a set of linear equations that look like this, right? So it looks like that. I'm gonna draw the non-zeros, right? Oh, sometimes people call this a SPI diagram. I have absolutely no idea why, but anyway, whatever. It doesn't matter. I'm just showing you the non-zeros, okay? Now, there's many other ways to understand this, and I'll show a couple. And the one's a way that's purely mathematical that you probably have all seen before, okay? So, and it also introduces a very interesting idea. I'll show you what that is. So let's take this one. Suppose you wanted to solve A plus BC, and the idea here is that B is like so this is low rank, looks like that, and here's A, and let's assume A has structure. So let's make A banded. That's because it's pretty and it has structure. So there's your sparsity pattern. That's A plus BC. Okay, A could be anything else. A could be sparse. A could be Fourier, DFT. It could be anything, it could be something that you have a fast transform for. It could be some wavelet thing or something. I don't care, right? And then, so the people would call this is like structured plus low rank. That's what this is. So it could be sparse plus low rank matrix or something. Okay. Now, the sparsity pattern of A plus BC is generally full. It's everything. That's because you just take B and C to be columns, or what B is a column and C is a row vector. Then it's just an outer product. It sprays entries all over the place, right? So then a generic method, there'll be no sparsity, nothing. So how you can solve these is very clever. And in fact, the first step, there's a name for it. It's actually called unelimination. So elimination means you take your variables and you look at one block and you say, I'm going to express that in terms of the others, then get rid of it. Unelimination means you're going to introduce a new one. So what you do is when you look at A plus BC, X equals B, you write that as A plus BY, right, equals B. Y is actually CX. Everybody got that? So that just, of course, they're the same thing. They're identical. But you rewrite these equations like that, right? So and here, so you've done unelimination. You've introduced new variables and new equations. Everybody got this? And you see this. Now, you're not trained yet, but you will be. And once you're trained, what you're searching for is the following: easily inverted matrices on the diagonal. And your eye should, once you're trained, go immediately to that minus I. It'll go immediately there, because in the world of easily inverted matrices, I is up there and minus I is up there. Okay, everybody cool? All right. Now, so you'd say, this is fantastic. I just learned about block elimination. I eliminate that block. Now, if you eliminate that block, you're eliminating Y, and where do you end up? Right back here. Everybody got it? So, well, duh. I mean, you uneliminated, and then eliminated the thing you just had introduced, right? Okay, fine. So the key is to control your urge, primal matrix structure factorization urge, to eliminate that minus I. And instead, you take this system and you eliminate A. And in fact, that's not a bad idea because the assumption here is that A is easy to invert, right? So A is a Fourier transform or some wavelet thing. I don't know what it is. It doesn't matter what it is, right? So that's what it is. Okay, if you eliminate A, so if you uneliminate, if you go from this to this, and then you eliminate A, not the minus I, you get this equation. And you will recognize that as the sure complement here, right? It's like, this thing minus that times the inverse of that times that, okay? Or the other way around. That's sure complement, okay? And you get this. Now, then you solve for AX. Once you get Y, you get X, okay? And you can actually write this out just purely mathematically, and it comes out to be this. A plus B C inverse is A inverse minus, and then this big old thing over here, okay? It's a very famous, it's got all sorts of names. Matrix inversion lemma, I think, is a nice one. We'll just do a quick example and then we'll quit for today. So if A were diagonal and B and C were dense, then that's a beautiful example, right? So that's called a diagonal plus low rank matrix, right? Perfect example of this structure, right? Then it says you can actually solve it in here. If you do the dumb method, it's like n cubed. If you use this method, which is an unelimination then an elimination, it actually ends up, it goes from cubic in n to linear in n, okay? So my claim is, these are not small differences, right? These are not theoretical things, right? The difference between knowing this and not knowing it, it means you can look at something and it can be a million by million set of equations. But if it's diagonal plus low rank, now you know. I can solve that probably in like sub-millisecond, but you have to know what you're doing.